Wonderful, guys. I'm going to do this sheet where we're going to do a bunch of questions, but because it's geometry, I'm going to intersperse this with some bits of theory. And I'm not going to gloss over the theory. Yesterday for number systems, we just did not touch any part of the theory. But now we're going to touch upon some bits of theory. But I'm going to rush through the theory. I expect you to know lots of bits of theory. It's going to be like a refresher rather than a class. And so let's start off straight away. It's going to be a reasonably fast-paced class. So hang on. And so vertically opposite angles are equal. Angles on a straight line add up to 180 degrees. We know this. And so then when there are two parallel lines, alternate interior angles are equal. Alternate exterior angles are equal. Corresponding angles are equal. Vertically opposite angles are equal. Co-interior angles are supplementary. And so two parallel lines cut by a transversal. And remember that this works both ways. If alternate interior angles are equal, then the lines are parallel. If the lines are parallel, then alternate interior angles are equal. The converse is also true. And so you can prove that two lines are parallel if you can establish that alternate interior angles are equal. Coming to triangles, bunch of very simple, very important properties that get tested in every exam. Sum of three angles is 180. Sum of any two sides is greater than the third side. And especially the second one kind of sneaks up on you. Sum of any two sides of a triangle is strictly greater than the third side. It's not greater than or equal to. It has got to be greater than. Remember that. And the next idea in any triangle, if one angle is greater than another angle, then the side opposite that angle will be the longer side. When the side opposite the larger angle is the longer side, the converse is also true. The angle opposite the longer side is a larger angle. Right? Remember, this property holds good only within a given triangle. You can't compare two triangles and plug in this property. Within one triangle, you can compare the opposite side and opposite angle. All three sides are equal, means equilateral triangle, isosceles triangle, scalene triangle. We know these definitions. Right angle triangle, obtuse angle triangle, acute angle triangle. Again, we know these definitions. I'm going to gloss over that. Pythagoras theorem, this is the mothership. Sum of the squares of the sides containing the right angle is equal to square of the hypotenuse. Right? This we know. So 3, 4, 5, 5, 12, 13, 1, 1, root 2. They're all triangles that are right angle. So sum of the squares of the two shorter sides will be equal to square of the longest side, which will happen to be the hypotenuse. And an extrapolation to this, if you have an acute angle triangle, where B is the longest side, A square plus C square will be greater than B square. If you have an obtuse angle triangle, where B is the longest side, A square plus C square will be less than B square. Right? So given three sides of a triangle or three angles of a triangle, you should straight away be able to say whether it's equilateral, isosceles, or scalene, right angle, acute angle, or obtuse angle. That you should know straight away. And what type of triangle it is, you should know. I'm going to skip this. The Pythagorean triplets 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40. The last one is not a Pythagorean triplet. A Pythagorean triplet is a set of three natural numbers that satisfy Pythagoras theorem. This is 1, 1. It's an isosceles right angle triangle. Sides in the ratio 1:1 root 2. Super. Now let's get to the real thing. We will be doing theory every now and then, but I don't want to do all the theory in one shot. So let's do a few questions and then we'll swing back to theory. How many scalene triangles exist with integer sides such that all three sides are factors of 12? And so whenever you're broadly given factors of 12, you can make the assumption they're integral factors of 12, whether infinitely many. And so how many scalene triangles exist with integer sides such that all three sides are factors of 12? These kind of questions are very common. So 1 unit of number systems, 1 unit of geometry. And that's prime testing territory. Simple idea. You're talking about a triangle. Sum of two sides has got to be greater than the third. All sides are factors of 12. List down all factors and then count carefully. Very simple. Give it a go. I'm going to wait for about half a minute to 1 minute, and then we'll go on to discuss this. We want all three sides to be factors of 12. We want this to be a triangle. Further, we want this to be a scalene triangle. I'm going to jump in and try to solve this. Factors of 12, 1, 2, 3, 4, 6, and 12. So I'm going to list them, all of them down. So we want the sides of the triangle to be integers from this 6. Straight away, you can eliminate 1, you can eliminate 12. If one side of the triangle is 12, the other two should add up to be more than 12. None of the other two factors can add up to be more than 12. That's out. And so if one of the sides is 1 and the other two sides are integers, they've got to be equal. And so if you have 1 as one side of the triangle and the other two are integers, then the other two integers have got to be equal. Otherwise, sum of two sides will never become greater than the third side. So 1 is out, 12 is out straight away. And so we're dealing only with 2, 3, 4, 6. From 2, 3, 4, 6, we'll have to extract 3 numbers, or you're effectively leaving out one of the numbers. So it could be 2, 3, 4, 2, 3, 6, 2, 4, 6, 3, 4, 6. These are only 4 possibilities, of which some might be a triangle, some might not be a triangle. And so 2, 3, 6, is that a triangle? That doesn't work. 2, 4, 6. So 2, 3, 6 doesn't work. 2, 4, 6 doesn't work. 3, 4, 6. So 2, 3, 6, 2, 4, 6. Both don't work. 3, 4, 6 works. Anything else that works? 2, 3, 4. So 2, 3, 4 and 3, 4, 6. 2 scalene triangles are possible where all 3 sides are factors of 12. It's a very regular question. So you need to be totally on top of this. Simple idea, factors of 12, scalene triangle, 3 distinct sides. Sum of 2 sides has got to be greater than the third one. Be methodical, be rigorous, don't miss something. These are the kind of questions where you should not rush through and get one detail wrong. Do it slowly, get that mark in the bag, go to the next one. So again, a very similar theme, but far tougher. So give it a go, tougher question. I'm going to give more than 1 minute, probably 2-3 minutes for this question. Wonderful question, tough question, give that a go. After about a minute and a bit, I'll give you a starting step, but try this question. Kind of question where the detail matters. So x, y, z are all integers. First idea. That forms sides of a triangle. Second idea. X into y is 4. Third idea. And this is the form sides of an obtuse angle triangle. That's a bunch of small things that you need to keep in mind. So sum of 2 sides has to be greater than the third side. That we know. We also know that if you square the 2 shorter sides and compare with the square of the longest side, the square of the longest side should be greater because it's an obtuse angle triangle. Finally, we're looking at 2 integers that multiply to give us 4. The third one also being some other integer. And so in these questions, it's very important to know what your starting step is. And you have to keep into account all of these little factors. Right? So for me, the best starting point would be x into y is 4. Find out what x and y could be. 2 integers multiply to give us 4. That's a good starting point. Stick that in. So we know what x and y could be. 2 of the sides, we know of possibilities. Then move to z with a bunch of trial and error and see if one condition is satisfied and the other is not. X into y equals 4. What are the possibilities? 1 into 4, 2 into 2. So 1 into 4, for the third side to be a triangle, what should be the third side? 4. If you have 1 and 4, if you have 1 as one of the sides of the triangle, then the other 2 sides being integers, they have got to be equal. 1, 3, 4, 1, 4, 5, 1, 6, 7 will never form a triangle. Sum of two sides has got to be greater than the third side. So if one of the sides is 1 and the other two sides are integers, the two integers have to be equal. So the only possibility is 1, 4, 4. Right? So now try out for 2, 2. So the one possible triangle we have in the bag is 1, 4, 4. Now we need to go to 2, 2. So 1, 4, 4 is a possible triangle. We still haven't come to that obtuse angle part. Right? The other possibilities are 2, 2 and what? 1, 2, 2, 2, 2, 2, 3, 2, 2, 4. Is it possible? So 2, 2, 1, 2, 2, 2, 2, 2, 3 are all possible. 2, 2, 4, 5, 6 are all not possible. 1, 4, 4 is possible. These are the possible triangles. Now we need to go to the part where we're worrying about the obtuse angle bit. 1, 4, 4. Is it an obtuse angle triangle? 1 square plus 4 square greater than 4 square. No. 2, 2, 1. 1 square plus 2 square greater than 2 square. This doesn't work. 2, 2, 2. An equilateral triangle. You don't have to worry. 2, 2, 3. 2 square plus 2 square is less than 3 square. It's a possible triangle. Product of two sides is 4. It's obtuse angle. All three sides are integers. This works. Nothing else works. That is 3. But a wonderful question, because there's nothing that's really difficult, but you have to put together a bunch of small ideas. And sum of two sides greater than the third one, two integers multiplying to give us 4, and then sum of the square of the two shorter sides less than square of the longest side. So 3 different criteria we put in into a simple framework. Very solvable, very much possible that you'll get a question like this. Be careful, don't rush through these. Be careful, don't miss out on some detail. Okay? Let's go to the next one. Revisit some theory. Theorems with triangles. Angle bisector theorem. If you have a line AD which bisects angle A, with D being on BC, then AB by AC equals BD by DC. The foot of the angle bisector divides the opposite side in the ratio of the sides containing the angle. Right? Remember, this works even when the bisector is bisecting the external angle. So if you have a bisector AE that bisects the external angle at A, this property would still hold good. Right? AB by AC is equal to BD by DC. Whether D is a foot of internal bisector or external bisector, it doesn't matter. Right? Just small things to remember. When you have this AD, very often, because it's the angle bisector, we tend to assume that it will be either perpendicular or it will bisect. It need not be either. From a vertex A, you can draw a line that bisects angle A. You can draw a line that is perpendicular to BC. You can draw a line that is to the midpoint of BC. Except in special case triangles, there will be 3 distinct lines. Remember that. Don't automatically mark BD and DC as same. It won't be. Basic proportionality theorem. If you have a line parallel to one side of the triangle, it cuts the other two sides in the same proportion. So if LM and AB are parallel, CL by LA equals CM by MB. Remember the triangles CLM and CAB are similar. We've not yet come to similarity in terms of our theory, but you guys know what similarity means. So CLM and CAB are similar. Area of a triangle is half into base into height. Base is any side of the triangle. Height is the corresponding altitude. That is the perpendicular line from the opposite vertex. So you can compute this in 3 different ways. Any side could be the base. The corresponding height we'll have to pick up and do that. Remember, half into base into height. For this, the height for the triangle need not be inside the triangle. So if you look at this triangle ADC, the height is still AE to the base DC. From A to BC, you can draw only one perpendicular. Fine. So altitude of a triangle can lie outside the triangle. Remember that. Don't forcefully draw a line from a vertex to the base. It could be to the base extended, either way. Let's keep that in mind. I've got this. Find the altitude to side AC of triangle with side AB equal to 20, AC equal to 20, and BC equal to 30. Two sides measuring 20 and the third one being 30. We want altitude to the side AC. We want to draw a perpendicular from B to AC and know how much it measures. This is an isosceles triangle, so that is very useful. So use that idea. This is an isosceles triangle. So for an isosceles triangle, from the unequal angle, if you draw a line perpendicular to the base, it will bisect the base. And use that idea. We need to find altitude to AC, which is the shorter side. So we need to find a perpendicular from B to AC and measure that. So, but it's an isosceles triangle. So I know that finding altitude AD is easy. So I forget that other altitude. Let's just find AD. We'll worry about that other altitude later on. So we know that if you draw a line from A perpendicular to BC, that will bisect BC. Why? For an isosceles triangle, if you draw a line from the unequal vertex perpendicular to the base, it will bisect the base. Why?
So the triangles are congruent.
Which triangles are congruent? ADB and ADC because of
Equal sides.
equal sides.
R is equal angle.
RHS, right angle, hypotenuse, and side are equal. So AD is common, AB and AC are equal, and the angle is 90 degrees. Because of RHS congruent, the two triangles are congruent. Therefore, BD will be equal to DC. So we found BD, we found DC. So now we know we can find AD. How do we find AD? Pythagoras theorem. Right, so right angle triangle, AD will be square root of 20 square minus 15 square. Let's just find AD. We're finding AD not because that's what being asked. That's easy to find. So let's find that. And then we'll worry about the perpendicular from B to AC. And so AD is square root of 20 square minus 15 square. So let's assume we have found that. We know that. Now you know AD. How do you find the other altitude? Area. Area is half into base into height. So area is half into BC into AD. It's also half into AC into that altitude. Area is equal. We are considering area of one triangle. So once we find this altitude, we can find that altitude. And in geometry, for some of these questions, whenever you start this question, you should know the whole approach. You should look at this question and say, I can find the simpler altitude that I need to find. Then area is equal, I'll find the other altitude. Once you know that, then you start off looking to find. Don't try to start on questions for which you don't know the whole method. Then you can get stuck somewhere. You find one bit and another part, but you really don't know where you are going. It's going to suck some time out of you. That's not worth doing. Geometry and coordinate geometry, you should pretty much know the whole thing or most of the distance when you're starting off the question. Right? So AD is 5 root 7, square root of 20 square minus 15 square, square root of 175. So 5 times root 7. 25 into 7 is 175. So we know AD is 5 root 7. We know that we want to find the other altitude. So half into 30 into 5 root 7 is half into 20 into altitude to AC. Half into 30 into 5 root 7 is half into 20 into H. So H is 3 by 2 times 5 root 7 or 7.5 root 7. And so if you know three sides of a triangle, if you know one altitude, you know all three altitudes. Area is half into base into height. So if you know one way you find the area, you can find it the other two ways as well. Right? So we'll go to the next question. Before that, a little bit more theory. Congruence and similarity, two very important ideas. Two triangles are said to be congruent if they are identical. Same shape, same size. Every metric of one triangle is equal to the corresponding metric in the second triangle. All sides are equal, all angles are equal, altitudes are equal, medians are equal, areas, perimeters, in radii, circumradii, everything is equal to the corresponding entity. Right? So similarity, two triangles are similar if they have the same shape, but not necessarily the same size. And so one is a larger or smaller version of the other. Every side metric is proportional. Every angle metric is equal. And every side metric will be in the same ratio. Every angle metric will be equal. And so how do you establish congruence? There are 4 rules. What are the 4 rules? SSS, SAS, ASA, RHS. And only 4 rules. There's no such thing as by similarity, by appearance, by symmetry and all that. If you're saying two triangles are congruent, you have to say one of these 4 things. Otherwise, they're not congruent. Right? And remember, it is SAS, it is side angle side, not 2 sides and 1 angle. The angle has got to be the included angle, the angle in between the 2 sides that happen to be equal. Likewise for ASA, but for ASA or AAS does not really matter. Why not? If 2 angles are equal, third angle will also be equal. Sum of 3 angles is 180. So ASA and AAS are both fine, but it has got to be SAS. It cannot be SSA. Similarity, 3 ways of establishing similarity: SSS, SAS, AAA. Again, SAS is side angle side. 2 sides are in proportion. Angle in between is equal. SSS, 3 sides are in the same ratio. AAA, all 3 angles are equal. Doesn't even have to be AAA, just AA. If 2 angles are equal between 2 triangles, third angles will be equal. If 2 triangles are similar, then all their side metrics are in proportion. If you're saying ABC is similar to DEF, then you can say AB by DE equals BC by EF equals AC by DF. This is called the similarity equation. Very often this is a starting point. You're going to say the 2 triangles are similar, so everything is in ratio. Altitudes are in ratio, the perimeters are in ratio. So you can plug that ratio and use that as a starting point. And to simplify this question, because you're going to use that, make sure you write down similar triangles in that orientation. What do I mean by that? ABC is similar to DEF. Make it a point to match vertices. Don't write FDE or FED. If you write that, then you're dead for the second equation. Be very careful. ABC is similar to DEF, and not FED. Keep that in mind. Now we know the sides are in ratio. Suppose we say that there are 2 triangles. The second triangle, every side is twice of the first triangle. The ratio of sides is 1:2. What will be the ratio of areas? 1:4. The sides will be double, altitude will be double. So area will become 4 times the first one. So keep that in mind. Super. We're going to build on this. We've spoken of congruence and similarity. We're going to talk about coming back to within a given triangle. So orthocenter of a triangle. Orthocenter is meeting point of altitudes. From a vertex, you draw a line perpendicular to the opposite side. That's the altitude. The 3 altitudes are concurrent. They meet at a point. They meet at a point called as orthocenter. Centroid. Centroid is a meeting point of medians. From vertex, you draw a line to midpoint of opposite side. That's a median. The 3 medians are concurrent. They meet at centroid. So meeting point of angle bisectors is in center. Meeting point of perpendicular bisectors, circumcenter. So with centroid, what is the other property that we have? Centroid divides each median in the ratio 2:1. So AG by GD will be 2:1. BG by GE will be 2:1. CG by GF will be 2:1. So centroid divides each median in the ratio 2:1. Orthocenter, centroid, in center, circumcenter. Circumcenter is meeting point of perpendicular bisectors. In center is meeting point of angle bisectors. With circumcenter as center, we can draw a circle that goes around the triangle or that circumscribes a triangle. This is called the circumcircle. The center of that circle is circumcenter. Radius of that circle is circumradius. Circumcenter, circumcircle, circumradius. Likewise, in center, in circle, in radius. Circumradius is denoted by capital R, in radius by small r. And so, in center, in circle, in radius, circumcenter, circumcircle, circumradius. Just a very quick recap of these properties. The median, altitude, and angle bisector start from a vertex. The perpendicular bisector has got nothing to do with the vertex. It's perpendicular bisector of the side. So if you're drawing a perpendicular bisector of a side of a triangle, make sure you don't draw it in a way where it has to pass through the opposite vertex. If it passes through the opposite vertex, then it's some kind of special triangle. In a triangle, if you draw a perpendicular bisector of a side, it need not pass through the opposite vertex. So keep that in mind. The other three start from the opposite vertex. Right? So in center and circumcenter are centers of the circle. Centroid and orthocenter. So centroid divides each median in the ratio 2:1. Keep that in mind. Let's go on to special case triangle. For a special triangle, we'll discuss all of these. Right? So if you have an equilateral triangle of side A, we want to find all of these. I'm going to find all of this, but before that, I'm going to jump in and discuss all the answer. Equilateral triangle of side A, area √3/4 a square. Perimeter, that is simple. Circumradius, a by √3. Right? In radius, a by 2 √3. Altitude, √3/2. Median, √3/2. And so altitude and median are same, √3/2. Area is √3/4 a square. Circumradius is a by √3. In radius is a by 2 √3. And so all of these you should know. I'm going to do a very quick recap of kind of deriving this. Equilateral triangle side AAA. We draw altitude from A to BC. This line will bisect BC. We've already seen this with the isosceles triangle. So BD and DC would be a by 2, a by 2. Once you've got that, we can use Pythagoras theorem and find AD. AD is √3 a by 2. AD happens to be the altitude, median, angle bisector, and perpendicular bisector. So a line from A to D bisects BC. It's perpendicular to BC. It's a perpendicular bisector of BC. It bisects angle BAC. So all four. So for an equilateral triangle, all four lines will coincide, not just from one vertex, from all three vertices. That means your incenter, circumcenter, orthocenter, and centroid are coincident. They're all the same point. So we can find that point. Now we know that point is also the centroid. Centroid divides that line AD in the ratio 2:1. So you can find the top part and the bottom part. And so the top part effectively is a by √3. AG is a by √3. GD is a by 2 √3. AG is circumradius. GD is in radius. We draw a circle around this triangle. G is the circumcenter. So it will happen to be the center of that circle that goes around. And from G, if you draw a circle with G as center, you draw a circle that passes through A, B, and C. GA or GB or GC will be the radius of that circle, which is a by √3. GD is the in radius, which is a by 2 √3. And so for our equilateral triangle, you should know all of these. Let's try this. Give it a go. These kind of questions are very common. The examiners love equilateral triangles. So if you're on top of the detail, you can just knock this off in minutes. This is a tough question, a really tough question, but you should be able to nail even this. So equilateral triangle inside a circle, circle inside equilateral triangle, square inside a circle, circle inside a square, equilateral triangle inside a square. All of those are prime testing territories. The wonderful symmetric shapes, 4 of them: equilateral triangle, square, circle, regular hexagon. So you should know everything about these. You have any 2 of these put together, you should nail that question. And so spend maybe 1 more minute, and then I'm going to rush through this question just so that you start thinking about it in terms of the numbers that we already know. And so you want to do this question without doing heavy duty framing of equations and writing down and stuff. And just glance, look at the data. What is there in this figure is enough to get everything that you want. going to put pressure on you. So let's go rattle off this question. Let's assume the big equilateral triangle has side A. Fine. So what is AP, the altitude? Root 3 A by 2. So what is the radius of the larger circle? A by 2 root 3. This is the inch circle. What is the diameter of the larger circle? A by root 3. Twice of in radius. And no, not rocket science. So I'm going to look at this line AP. Again, no pen on paper. We're doing this. Fine. So AP is root 3 A by 2. PQ is A by root 3. So what is AQ? A by 2 root 3. The remaining part. So AQ plus PQ is AP. AP is root 3 A by 2. 1/3 of that is in radius. 2/3 of that is PQ. So remaining should be 1/3 of that, which is A by 2 root 3. Fine. So AQ is A by 2 root 3. All we want to find is the in radius of the smaller circle in terms of A. Then we're done. Right. So AQ, we know, we can find it. Forget even what we have found out. AQ we can find. That much we know. What fraction of AQ is O2Q? AQ is 1 by 2 root 3. A by 2 root 3. O2Q as a share of AQ. What is O2 to the small triangle? 1 by? See, O2Q. See, this O2Q is in radius of the small triangle ADE. Right? So forget about A by 2 root 3. Then we have to find the side of the triangle. Forget that. AQ is the median of the small triangle. What is O2Q in terms of AQ? 1 by 2 or 1/3? 1/3. So O2Q is 1/3 of AQ. I'm deliberately not writing anything this on paper, but I want you to follow this thread. What we are doing here, we are finding AP, root 3 A by 2. We know PQ, A by root 3. From root 3 A by 2, we subtract A by root 3, we can find AQ. AQ is A by 2 root 3. If you know AQ, O2Q is 1/3 of that. So O2Q is the radius that we need to find. Is 1/3 of A by 2 root 3. And then you're done. You've got the radius that you need to find in terms of side of the equilateral triangle. And I'm going to go over the whole process again. AP is root 3 A by 2. That you should know. There's no way you can not know that. Fine. So in radius of the large circle, basically radius of the large circle, which is in radius of the equilateral triangle, that you know, A by 2 root 3. But we don't want just the radius, we want the diameter. That's what we're going to remove. Fine. So PQ is a diameter, which is A by root 3. We remove A by root 3 from root 3 A by 2. We get AQ, which is A by 2 root 3. AQ is A by 2 root 3. That we have found. AQ is the altitude for the smaller equilateral triangle. It's not just the altitude, it's also the median. O2 is the centroid for that triangle. Because the circumcenter, because it's in center, an equilateral triangle. So O2 divides AQ in the ratio 2:1. Or O2Q is 1/3 of AQ. We know AQ is A by 2 root 3. O2Q is 1/3 of A by 2 root 3. So we've got the radius in terms of A. Then finding the area is simple. Pi r square is area, root 3 by 4 A square is area. Then find the ratio, simplify all of that. And so you should know every number for an equilateral triangle. So once you get to the small triangle, you should just be rattling off the same ideas. Fine. So we are not even finding the side of the smaller equilateral triangle, ADE. You don't need to find that. If you have to, the other approach would be to say altitude is A by 2 root 3. With that, I can find the side. From that, I find the in radius. Using altitude, you find the side. Using the side, you come back to the in radius. Fine, but we can even bypass that because O2Q is 1/3 of AQ. We know that. So once you find AQ, 1/3 of that is O2Q. Then plug in root 3 by 4 A square as area of equilateral triangle. Pi r square is area of small circle. You're done. And so the key point here that I'm emphasizing over and over again, you should totally, completely, comprehensively know your A by root 3, A by 2 root 3, root 3 A by 2, that thing. Root 3 A by 2, 1/3 of that is in radius. 2/3 of that is circumradius. That's where it all begins. So root 3 A by 2, 1/3 of that is in radius. 2/3 of that is circumradius. That's why we are able to say PQ is 2/3 of AP. AQ is 1/3 of AP. And O2Q is 1/3 of AQ. So once you get that ratio, you're just nailing this question. Fine. So you should know all these details. Fine. So when you're doing, you might have with pen on paper, you might be more comfortable writing the number down and seeing that and visualizing that. But But you should know a by root 3, a by 2 root 3, all of that really well. So stay on top of equilateral triangle and a circle placed inside that or around that. And just to recap, diameter of larger circle is a by 2 root 3. So altitude AD is root 3 a by 2, RD is a by root 3. So AR is a by 2 root 3. We found that. AR is 1/3 of AD. We know that. So we found AR, then we can find radius of the smaller circle. Once you know radius of smaller circle, you can simplify the rest. We've done everything, all of these properties in center, circumcenter, in radius, circumradius, all of that for an equilateral triangle. Just going to do an extrapolation of this. Think of a right angle triangle and then find out all of these points. Right? So before that, centroid is meeting point of median. Orthocenter is meeting point of circumcenter is meeting point of perpendicular bisector. In center is meeting point of angle bisector. So let's take this right triangle ABC. The sides of the triangle, let it be A, B, and C, with B being the hypotenuse. Now we draw an altitude from A to BC, B to AC, and C to AB. Where will the altitudes meet? So for any right angle triangle, the orthocenter is the vertex containing the right angle. For this right angle triangle, right angle at B, the orthocenter is at B. For any right triangle, orthocenter is the vertex containing the right angle. You should know that vertex containing right angle is a meeting point of 3 altitudes. AB is the altitude from A to BC. CB is the altitude from C to AB. The altitude from B goes through B. The other two meet at B. So the orthocenter has got to be B. Now we found the orthocenter. Now let's move to the circumcenter. Let's draw a circle around this triangle. If we draw a circle around this triangle, this AB, BC, and CA are chords of the circle. Right? Now this AC is a chord which, funnily enough, makes an angle of 90 degrees on the circle. So AC is a diameter. So center will be, which is also what for the triangle? Circumcenter. So circumcenter of a right angle triangle is midpoint of hypotenuse. For any right triangle, orthocenter is the vertex containing the right angle. Circumcenter is midpoint of hypotenuse. Circumradius is half of hypotenuse. The hypotenuse is the diameter of the circumcircle. Or 2 times circumradius is hypotenuse. Or circumradius is half of hypotenuse. So this line B to midpoint of AC, that BO. O is the midpoint of AC. So if we take this point O here, that is a circumcenter. AO is equal to OC is equal to R, circumradius. BO will also be R, because O is the center of the circle, B is a point on the circle. So AO is equal to BO is equal to CO, all three equal to circumradius. So once you have got this going, then this line BO is a fabulous special line. BO is the circumradius, which is nothing but half of hypotenuse, that we know. Right? What is B for the triangle? Orthocenter. So BO is a line joining orthocenter to circumcenter of a right angle triangle. And PO is a line from B to midpoint of AC. So it's a median to AC. So median to the hypotenuse is also BO. So if you have a right angle triangle with hypotenuse given, then circumradius is half of hypotenuse, which is nothing but the distance between orthocenter and circumcenter, which is nothing but median to the hypotenuse. In any right triangle, median to the hypotenuse is half of hypotenuse. And so all four can be linked together like this.
This line need not be perpendicular to that.
You tell me. It need not be. It will be perpendicular only if it's an isosceles triangle. Median need not be altitude. It looks like it is, but it's not. It need not be. So all these ideas you should know. Any right angle triangle, orthocenter is the vertex containing the right angle. Circumcenter is midpoint of hypotenuse. Circumradius is half of hypotenuse. That circumradius, which is half of hypotenuse, is also equal to the distance between orthocenter and circumcenter, which also happens to be length of median to the hypotenuse. So if you get anything in right angle triangle and circumradius, hypotenuse, any of that, you should just nail that straight away. And so for this right angle triangle, I know we have not done this part of the theory yet. What is the sides are A, B, and C, with B being the hypotenuse. What will be the in radius?
A plus B minus, sorry, A plus B. Some of the other sides minus hypotenuse.
Sum of the two sides minus hypotenuse by 2. So it is A plus C minus B by 2. Sum of the two right angle holding sides minus the hypotenuse by 2 is in radius. Half of hypotenuse is circumradius. Right? So in radius, circumradius, orthocenter, circumcenter, those ideas in a right triangle, you should be on top of completely, comprehensively. Right? So let's go to the question. Next question is being completely set up. Right? So just read the question, give the answer, and then we'll go to the next one. The sides of a triangle measure 9, 40, and 41. Then what is the measure of the line segment that joins the orthocenter and the circumcenter of this triangle? Orthocenter to circumcenter is circumradius, which is half of hypotenuse, half of 41, 20.5. First up, the moment you read this question, you see 9 and 40, you should be looking for 41. 9, 40, 41 is a wonderful Pythagorean triplet. Your eyes should go wide open and say, look, right triangle. Now I know everything here. So this is a right angle triangle. So the line joining orthocenter and circumcenter of this triangle is nothing but circumradius, which happens to be half of hypotenuse, 41 by 2, 20.5. You're done. And you will get questions like this. If you get one such question, then you've got a huge advantage, because this is all mumbo jumbo. Someone who doesn't know this fun fact just can't answer this question. Whereas you can answer this in like 30 seconds. You read the question, you write down the answer, you go to the next one. Right? We'll move on to circles. Circles described by center and radius. So this line AB is called the arc of the circle. That part there, which resembles a pizza slice, is a sector of the circle. You have minor arc and major arc, minor sector and major sector. AB, the straight line, is called chord of the circle. The part below that is called the segment of the circle. The remaining is called the major segment. So you have minor arc and major arc, minor sector, major sector, minor segment, major segment. So, and AB is a chord of this circle. What type of triangle is triangle AOB? Isosceles, 2 radii. So from O, if I draw a line perpendicular to AB, what can I say about it? Bisect. So from center of a circle, if you draw a line perpendicular to a chord, it will bisect the chord. From center of a circle, if you draw a line bisecting a chord, it will be perpendicular to the chord. If you want to draw a line to the midpoint, it will happen to be at 90 degrees. If you want to draw it to be at 90 degrees, it will happen to bisect. The third way of stating the same idea, if you draw the perpendicular bisector of a chord, it will pass through the center of a circle. You draw the perpendicular bisector of AB, it will pass through O. So 3 ways of stating the same idea, and that's very important. So because of that property, this triangle OFB that we see, that is a right angle triangle. Therefore, OF square plus FB square is OB square, Pythagoras theorem. In practically every question in circles which got to do with distances will be using Pythagoras theorem. So in circles, the mantra is very simple. Look at the circle, look to find a right angle, complete the right triangle, plug in Pythagoras theorem. It's going to be one flood of Pythagoras theorem. Every time you see a right triangle, plug in Pythagoras theorem. If you can't find a right triangle, look for a right angle, find the right triangle, plug in Pythagoras theorem. Every question in circles will have that. So keep that in mind. You're chasing for Pythagorean numbers. 2 circles touch each other internally like the first diagram, externally like the second diagram. Right? So now we're going to push it. I know we have not done the theory on tangents today, but you know what tangents are. And so for the first type of diagram where 2 circles touch each other internally, how many common tangents can be drawn? For second one, 3. One on the top, one on the bottom, one bang in the point of contact. So your question might not say 2 circles touch each other internally. They could say 2 circles C1 and C2 have a common tangent at B. That means the circles touch each other internally. If 2 circles have 2 points of contact, then they are said to intersect with each other. So circles like this are intersecting with each other. That line segment AB is a chord to both circles, or it's called a common chord. If you draw perpendicular bisector of AB, what do we know about that? It will pass through O1 and O2. Or line joining the centers of 2 intersecting circles is the perpendicular bisector of the common chord. Saying it the other way around. Right? If you have 2 intersecting circles, how many common tangents will be there? 2. So 2 circles can have 1 common tangent. That means they're touching each other internally. 2 common tangents. That means they intersect with each other. 3 common tangents. That means they touch each other externally. Can 2 circles have 4 common tangents? Can 2 circles have 4 tangents that are common to both of them? How will be the diagram? 2 disjoint circles. 2 circles that are disjoint, nothing, no overlap at all. 1 tangent on top, 1 on bottom, what are called as transverse tangents. going from top to bottom, from top to bottom. So that's a scenario where two circles can have 4 common tangents. And so what type of circles you have can be defined with these. You can say two circles have exactly 2 common tangents and radii 4 and 5. Find the distance between their centers. Okay. That means you have to draw 2 circles that intersect with each other and then figure out something else after that.
4 is the maximum.
You tell me. 4 is the maximum. So 2 circles can have 1 common tangent, 2, 3, or 4. Can 2 circles have 0 common tangents? No common tangents at all. One is inside another. So if 2 circles have 0 common tangent, then 1 circle is completely contained inside another. So you should know all 5 scenarios where circles have 0, 1, 2, 3, 4 common tangents. One property with angles. Angle at the center is twice angle on the segment. So if a circle is like this, angle AOB is equal to angle AEB equal to angle ADB. Direct takeaway from this, angle in the same segment are equal. Angle AEB is equal to angle ADB. Any point you find on arc BA, the major arc, it will make the same angle between A and B. Right? But remember, angle at the center is AOB, angle on the segment, the point should lie on the major arc. If you put it on the minor arc, then the angle at the center is the reflex angle. So if you're talking about this as the angle on the segment, this is the angle at the center. If you talk about this at the angle at the center, then this will be the angle on the segment. Right? So what is the angle at the center? What is the angle on the segment? You should know. Vital. Take away from this, angle at the center is twice angle on the segment. So if you find the diameter, what is angle AOB? 180. So angle ADB? 90. Angle in a semicircle is a right angle. If you have a shape like this, AEBD is called a cyclic quadrilateral. Any 4-sided shape is a quadrilateral. We know that. 4-sided shape where all 4 vertices lie on the circle is a cyclic quadrilateral. So if you have a cyclic quadrilateral, then if angle ADB were x, then angle AOB would be 2x. If angle AEB were y, angle BOA, the reflex angle, would be 2y. 2x plus 2y? 360. So x plus y? Opposite angles of a cyclic quadrilateral are supplementary. When angle in a semicircle is a right angle, opposite angles of a cyclic quadrilateral are supplementary. And 2 very important angle properties. One chord property, product of the rectangles formed by 2 intersecting chords is equal. And what goes in this? If you have 2 chords AB and CD intersecting at E, AE into EB equals CE into ED. AE into EB equals CE into ED. Right? Just one point to elaborate on this. This holds good even if 2 chords intersect outside the circle. Here we have 2 chords AB and CD. They meet inside the circle. If they intersected outside the circle, still the property would hold good. AE into EB equals AE into EB is equal to CE into ED.
Outside the circle, how?
Then there'll be secants. If the 2 chords meet outside the circle, that means that they meet from an external point. So from an external point, you're drawing 2 chords which cut the circle at 2 points. They're effectively secants. Even for secant, this property will hold good. Then you move on to tangents. From a point outside the circle, you can draw 2 tangents to the circle and only 2 tangents. The 2 tangents will be equal in length. The 2 tangents will be perpendicular to the radii. Tangent is perpendicular to radius at the point of tangency. And there the tangent meets the circle. At that point, if you draw the radius, tangent will be perpendicular to radius. Right? So again, we have Pythagoras theorem. OT square plus PT square is equal to OP square. And so every question in circles, whether within a circle or with tangents involved, you'll have right angles, right triangles, Pythagoras theorem. So keep an eye out for that. Don't ignore Pythagoras theorem. So whenever you do anything on circles, there should be a track that goes in your mind, which is maybe some Pythagoras theorem is going to be useful somewhere. So stick in Pythagoras theorem whenever possible. That will work. So keep that in mind. With circles, an extra theorem, which is tangent secant theorem. Square of the tangent is equal to product of the secants. PT square equals PA into PB. Remember, it is PA into PB, not PA into AB. P to A, P all the way to B. Which is why if you have PT square, PAB and PCD, PT square will be equal to PA into PB, and PC into PD, or PA into PB is PC into PD, which is our two chords intersecting outside the circle. The same idea. Fine. So the chords intersecting part and tangent secant theorem, probably the same idea we're discussing. Have a go at this. Tough question. Give it a go. Do all of you have the sheets? Wonderful question, possibly on the tougher side, incredibly tough diagram to draw. And in almost all questions in geometry, it's very unlikely that you'll be given a wonderful handy diagram to boot. And so you need to speak the language. So triangle PQR inscribed inside a circle. Altitude from P to RQ extended meets RQ at S and is a tangent to the circle. So it's very tough to just draw this diagram well. But you need to understand altitude from P to RQ extended. What does that mean? What it says about the angle? Circle inscribed inside, sorry, triangle inscribed inside a circle. Tangent to the circle. Each of those things means something. So even if you're under time pressure, don't rush through the diagram drawing part. This question is doable only if you have a wonderful diagram. If you get the diagram wrong, it's a classic wild goose chase. I spent 10-12 minutes trying to solve this question, but I had the wrong diagram, so I went nowhere with it. So pause, go slowly, capture all information in that good diagram, and then go. If you're not able to do this, dump the question, because there's lots of detail that's sitting in there which says the diagram has got to be spot on. So use all of that and draw an appropriate diagram.
Is it transfer?
You're drawing an altitude from one vertex to a side of a triangle, and it falls on the line extended. What does it mean? Obtuse angle. So altitude from P to RQ meets RQ extended. That means angle at Q is obtuse angle. If it meant QR extended, then angle at R is obtuse angle. You can imagine the diagram, draw the diagram and get that. So this is telling us that angle PQR is obtuse angle. So you have an obtuse angle triangle inscribed inside a circle. Sorry, P? SP is the tangent. We'll discuss this one wonderful question. So you have a triangle PQR inscribed inside a circle. Altitude from P to RQ extended meets RQ at S. So S lies outside of RQ. It does not lie on RQ. It lies on RQ extended. We know PQR is an obtuse angle triangle, and RQ extended to S, and PS is perpendicular to RS. And so we're drawing an altitude from P to RQ. The foot of the altitude cannot lie on RQ. It can lie only on extension of RQ, which happens to be this point S. And we've also been told that SP is tangent to the circle. And so this altitude happens to be the tangent to the circle. Obviously, it's not tangent at S. It's tangent at P. P is a point on the circle. So SP is a tangent. And so once you've drawn this diagram, which is incredibly tough, if you know that SP is a tangent, we can say SQR is a secant and SP is tangent. SQ into SR is SP square. So SQ into SR is 8 into 18, which is 144. This is SP square, or SP is 12. SP is the altitude, QR is the base. You've got the area. Area is half into base into height. Base is QR, which is 10. Height is SP, which is 12. So area is half into 12 into 10, which is 60. It's just 12 into 10 into 12. It is 1 by 2 into 10 into 12, which is 60 square centimeters. Okay. Areas, once you know the altitude, we can find the area. That part is simple. The most critical part in this entire question is getting that diagram right. You know there's an obtuse angle triangle. Therefore, the triangle is small. It's in one part of the circle. If you draw a large triangle, which takes a big part of the circle, then constructing and imagining this tangent and altitude becomes very tough. But if you draw a triangle where PQR is obtuse angle, then it's easier. So you extend RQ to go to S, and PS is perpendicular to SR. SP is the tangent to the circle. If you get both of those ideas right, then we know that PS we find, we are through. Because we know the base, we find the height, we are through. How do we find PS? SP square equals SQ into SR. Square as a tangent is equal to product as a secant. So SP is 12, RQ is 10, half into 12 into 10, that's the area, which is 60 square centimeters. One more theorem on tangents. It's called the alternate segment theorem. Angle made between tangent and chord is equal to angle made by the chord in the other segment. So if you look at the chord AB, then on tangent AP, this angle here is equal to the angle made by this chord in the other segment, this point X. So angle BAP, if it were X, then angle BCA would also be X. Angle between tangent and chord is equal to angle made by the chord in the other segment. Because it's saying other segment, it's called alternate segment theorem. How do we prove that? Think about it. Have a center as X, center as O. If this angle BAP were X, then angle BAO would be 90 minus x. Tangent is perpendicular to radius. So OAP is 90. This is x, that is 90 minus x. What type of triangle is triangle OBA? Isosceles. So OAB is 90 minus x. OBA will also be 90 minus x. So what will be angle BOA? 2x. So angle BOA is 2x. If BOA is 2x, BCA would be x. The choices are wrong. Forget the choices. Find the answer. Two circles with radii 3 centimeters and 6 centimeters have centers that are 9 centimeters apart. What does this mean? They touch each other externally. The same question could have been given as two circles with radii 3 centimeters and 6 centimeters have exactly how many tangents? 3 common tangents. So other way of saying that touch each other externally. So the question can say two circles with radii 3 and 6 touch each other externally, or it can say radii 3 and 6 have their distances 9 centimeters apart, or it can say two circles of radii 3 and 6 have exactly 3 common tangents between them. All three mean the same thing. Different ways of defining that question. Once that is done, then you can simply draw the diagram. Actually, once you draw the right diagram, this question is a walk. It's a very simple question if you draw the right diagram. When you draw the diagram, mark as much detail on it as possible. We want to find AB. Finding AB is tough, at least not that easy. First things to note, what is angle PAR? 90. Why? Tangent is perpendicular to radius. And so, therefore, angle QBR is also 90 for the same reason. And so, QBR is 90, QAR is PAR is 90. Both are 90 degrees. So now we know that PQ is 9, PA is 6, QB is 3. All that we know. Right? What can you say about triangles PBQ and RBQ and RAP? Similar. Two angles are 90, one angle is common. And so these two triangles are similar. Start with that and build on that. Once you have found these two triangles are similar, it's a very simple question. And so what is the ratio of the sides? 1:2. So we know that BQ by AP is 1:2. Or can we say RQ? What is that equal to? 9. PQ is 9. RQ should be 9. If this were X, this will also be X. AR is twice of BR. This is X. The whole thing should be 2X, or AB is X. Or this is the midpoint of RA. Q is the midpoint of RP. So if this is 9, QB is 3. We find X, we find this. If we find BR, we can find AB. Both are equal. How do you find BR? Pythagoras theorem. So square root of 9 square minus 3 square. Root 72. That's your answer. And so BR square plus QB square is RQ square. And so in this tangent thing, make sure that you know where the right angle is. I've seen many questions go wrong where the equation is written as QB square plus QR square is BR square. We're used to drawing a diagram where the hypotenuse comes on the right hand side top. In this question, the hypotenuse is not BR, it is QR. Remember that? So we are used to drawing a triangle BQR where the right angle is at Q. Here the right angle is at B. So keep that in mind. Once you keep that in mind, BR is square root of 9 square minus 3 square, which is root 72. BR is nothing but AB, which is what we need to find. And once you've figured out similarity and you know the ratio of the sides is 1:2 because BQ is half of AP. Once you find that, we know that QR is half of PR, or QR is equal to PQ. PQ is 9, QR is 9. Once you know QR, you can find BR. BR is same as AB, square root of 72. Try the next one. This again is a tough question. This again is a tough question. We need to figure out what is the minimum value of PQ. And so not just asking us for the answer, try to find out something related to minimum value of PQ. And so we'll get to PQ. Let's find MS, RS, find what RT is, what TS is. We'll find whatever we can find, and then we'll go to finding minimum value of PQ. So think about filling some detail, getting some values in, then we'll go to finding minimum value of PQ. RS is a distance of 3 units from the center of radius of the circle of radius 5 centimeters. The radius OS is 5, the distance OM is 3. So MS would be 4. RS is, so we know that TS is 1/3 of RT. So what is RT? What is TS? 6 and 2. So RT is 6, TS is 2. That much we know. We need to find minimum value of PQ. How do we do this? Sorry? Okay, TP into TQ equals TR into TS. Okay, so TR into TS is 12. So TP into TQ is 12. That we know. So PT into PQ is, sorry, PT into TQ is 12. How do we find minimum value of PQ from that?
You can find cases, it can be either 112, 26,
okay.
4
Okay.
Minimum is 4 plus 3.
Why not 12 by 5 into 5? So you're thinking integers. Don't think integers. Why can it not be 12 by 7 into 7? Which both should be equal? PT and TQ should be equal. So only when they are equal will the sum be minimum. Or we're using the idea that PT plus TQ by 2, which is the arithmetic mean, is always greater than or equal to the geometric mean, which is PT into TQ. See, formal way of doing it, arithmetic mean is greater than or equal to geometric mean. We know PT into TQ is 12. What is the maximum value PT plus TQ can? What is the minimum value PT plus TQ can have? That will be there when both are equal. So what should be PT? What should be TQ? Root 12 and root 12. So PT should be square root of 12. TQ should be square root of 12. Or PQ is 2 times square root of 12 or 4 root 3. That's a wonderful question because we can get to PT into TQ. We still have no way of finding PT plus TQ. Given PT into TQ, PT plus TQ will be minimum when they're equal. So PT should be root 12, TQ should be root 12. So root 12 plus root 12, that's the answer we're looking at. So 2 times root 12 or 4 times root 3. In the formal way of doing this, PT plus TQ by 2 is greater than or equal to square root of PT into TQ. Or square root of PT into TQ is root 12. So PQ is greater than or equal to 2 times root 12. Or the minimum value PQ can take is 2 times root 12. This inequality is called arithmetic mean, geometric mean inequality. Arithmetic mean of any set of numbers is greater than or equal to geometric mean of same set of numbers. Remember, the numbers have to be real and positive. They need not be integers, they need not be rational numbers. When any set of numbers you have, arithmetic mean will be strictly greater than or equal to geometric mean. This holds good whenever the numbers are real and non-negative, real and positive. It cannot be negative. Two negative numbers, there's no such thing as geometric mean. Okay? So you have real and positive numbers. Arithmetic mean of any set of numbers is greater than or equal to geometric mean. The extension to this is equality holds good only when all numbers are equal. If arithmetic mean is equal to geometric mean, then all the numbers should be equal. Whether you're talking about 2 numbers or 3 numbers or 4 numbers, it doesn't matter. If arithmetic mean is equal to geometric mean, that means all numbers are equal. I'm going to shift back to theory a little bit because we have done tangents. So let's come back to right angle triangle. We know that if you have a right angle triangle with sides AB and hypotenuse H, what is the circumradius? H by 2. So circumradius we know is H by 2. Now we're going to try to find in radius. And so if you draw a circle inside this, the circle will break each of the sides of the triangle into 2 line segments each. And so when you're talking about each of those line segments, they're all tangents from external points. So AD is equal to AE, CD is equal to CF, BE is equal to BF. If you call this as X and X, Y and Y, Z and Z, we know that X plus Y is A, Y plus Z is H, and X plus Z is B. So we can find X, Y, Z in terms of ABCs, AB and H, that we can find. So let's keep it at that. Now, if you draw the line from the in center to each side of the triangle, if you draw the 3 radii, we know that the 3 radii are perpendicular to the 3 sides. So from in center, if you draw radius ID and IF, what shape is DIFC? Square. DIFC is a square. 2 radii, all 4 right angles, radii are equal, the tangents are equal. Or effectively, this X that we try to find is nothing but in radius. Right? So if you look at the equations, we have X plus Y is A, Y plus Z is H, X plus Z is B. It says A, should be B. So from here, we want to find X. X will happen to be A plus B minus H by 2. And so for a right angle triangle with sides A and B and hypotenuse H, in radius is A plus B minus H by 2. Circumradius is H by 2. In radius is A plus B minus H by 2. Both you should know. Any right triangle A, B, and H, in radius is A plus B minus H by 2. Before we go on to the rest of the questions, I want to do one more bit of theory. We'll finish off theory and then carry on with the questions. I don't want to rush through the theory part. Right? So we've done a lot of questions with triangles and circles. Now we're going to move on to quadrilaterals. Right? Starting point, quadrilateral parallelogram. A parallelogram is defined as a shape where opposite sides are parallel. Opposite sides are parallel, they'll also happen to be equal. In any parallelogram, opposite sides will be parallel and equal. Opposite angles will be equal. All pairs of adjacent angles will be supplementary. And so these two, the top 2 angles add up to 180, the right 2 angles add up to 180, bottom 2 angles add up to 180. Opposite angles are equal, adjacent angles are supplementary. On top of all of these, the diagonals of a parallelogram will bisect each other. Diagonals bisect each other. AO is equal to OB, OC, BO equal to OD. A special case of a parallelogram is a rhombus. A rhombus is a parallelogram where all 4 sides are equal. Again, opposite sides are parallel and equal, opposite angles are equal, adjacent angles are supplementary. Everything holds good. Everything that holds good for a parallelogram will necessarily hold good for a rhombus. So diagonals of a rhombus bisect each other. On top of that, diagonals of a rhombus are also perpendicular to each other. So diagonals of a rhombus are effectively perpendicular bisectors of each other. Another special case of a parallelogram is a rectangle. A rectangle is a parallelogram where one angle is 90. All 4 angles are 90. Again, everything that holds good there will hold good here. The diagonals will bisect each other. Diagonals will also be equal to each other. When both of these special conditions are met, we get a square. In a square, all sides are equal, all angles are equal, all the diagonals are equal, the diagonals bisect each other, the diagonals are perpendicular to each other. The square is the most symmetric of quadrilaterals. Square is the regular quadrilateral. A trapezoid or trapezium is a shape where one pair of sides, opposite sides is parallel, the other one will not be parallel. If that also happen to be parallel, we'll be back to a parallelogram. Right? So in any trapezium, the diagonals cut each other in proportion. AO by OC equals BO by OD. Again, it's nothing but similarity. Two triangles are similar because adjacent angles are vertically opposite angles are equal, alternate interior angles are equal. So triangles will end up being similar, so they cut each other in the same proportion. A trapezoid where the non-parallel sides are equal is called an isosceles trapezoid. It's a symmetric shape. The 2 base angles will be equal, the 2 top angles will be equal. And remember, the pair of parallel sides should not be equal. If one pair of sides are parallel and equal, we'll again end up at a parallelogram. One pair of opposite sides is parallel, the other set of opposite sides is equal. Those are called the legs of the trapezium. The isosceles trapezoid has a symmetric shape where one pair of sides is equal, the other pair of opposite sides are parallel. An isosceles trapezoid can be broken into an isosceles triangle and a parallelogram. A kite is a shape where 2 pairs of adjacent sides are equal. In a kite, also the diagonals will be perpendicular to each other. In a kite, one diagonal will bisect the other. If you look at this kite, the diagonal BD bisects AC and it's perpendicular to AC. So BD is the perpendicular bisector of AC. So the diagonals are not perpendicular bisectors of each other. One is the perpendicular bisector of the other. The perpendicular bisectors of each other will be sitting on a rhombus. Triangle BAC and triangle DAC are both isosceles. On one diagonal AC, you have an isosceles triangle on top, isosceles triangle on bottom, you get a kite. A special case of a quadrilateral is a cyclic quadrilateral. Opposite angles of a cyclic quadrilateral are supplementary. Quadrilateral that circumscribes the circle, or a quadrilateral that goes around a circle. In this type of quadrilateral, the sum of pairs of opposite sides is equal. AB plus CD equals AD plus BC. Polygon. Say we extrapolate quadrilateral, we say n-sided shape. A four-sided shape is a quadrilateral, 5 sides is pentagon, hexagon, heptagon, octagon, nonagon, decagon. And so these terms you should know. Any n-sided shape is called a polygon. With polygons, there are 3 important properties. First one, the angle which is inside is called the internal angle. Angle outside is called the external angle. In any polygon, if you add all the external angles, what will you get? 360 degrees. Sum of all external angles of a polygon is 360 degrees. Internal plus external angle at each vertex adds up to 180. So sum of all internal plus external angles is 180 into n, or sum of all internal angles is 180n minus 360, or 180 into n minus 2. For any polygon, sum of external angles is 360 degrees. Sum of all internal angles is 180n minus 360 degrees. Any n-sided polygon will have n into n minus 3 by 2 diagonals. From each vertex, you will have n minus 3 diagonals. So n into n minus 3 total diagonals. But here we are double counting everything. So n into n minus 3 divided by 2. A regular polygon is a polygon where all sides are equal and all angles are equal. All internal angles are equal, all external angles are equal. A regular pentagon would have each external angle is 72 degrees. Each internal angle is 108 degrees. So any regular shape, you can find each internal angle, each external angle, all of that. A regular hexagon is a wonderful shape because each internal angle is 120 degrees. Each external angle is 60 degrees. So a regular hexagon is nothing but 6 equilateral triangles placed around the center. So regular hexagon of side A, what will be the area? 6 into root 3 by 4 a square. What will be the circumradius of this regular hexagon of side A? A. Circle going around it. Circle will have center O, radius A. What will be the in radius of this regular hexagon of side A? Root 3a by 2. In radius is a circle just inside this regular hexagon. So each side of the hexagon will be tangent to that. So in radius is effectively altitude of that equilateral triangle, root 3a by 2. So once you know everything about equilateral triangle, you know everything about regular hexagon straight away. Complete the theory and we'll come back to this. Area of a triangle is a very interesting set of formulae. Area of a triangle is half into base into height. It is also equal to half into BC sin A, product of two sides of a triangle and sine of the angle in between. It's equal to square root of S into S minus A into S minus B into S minus C. It's also R into S, where S is semi-perimeter, R is in radius. It's also equal to ABC by 4R. And so all of these are formulae for area of a triangle. Very often we'll use more than one of these to find something else. So if you're given an equilateral triangle, it's very easy to find in radius or circumradius. Suppose you're given a triangle which measures side 13, 14, 15. How will you find the in radius? 13, 14, 15. How do we find in radius? Find semi-perimeter. Okay. For how do you find area? Ground formula. Root of S into S minus A into S minus B into S minus C. Use that, find area. Use the formula R into S to equate this area. You know S, you know area, you can find R. And so we can use all of these formulae in sets in pairs to find different bits about the triangle, in radius, circumradius, semi-perimeter, area, all of that. And so we're going to round this off by adding one bit of trigonometry and then establishing each of these, drawing the links across them. First one, any triangle, we're going to use a little bit of trigonometry. It helps to know the sine rule. A by sine A is equal to B by sine B equal to C by sine C is equal to 2R, where R is the circumradius. And this is called the sine rule. Any triangle A by sine A will be equal to B by sine B equal to C by sine C equal to 2R. Okay. I'm going to see how this is true. Right. You take a triangle ABC, draw a circle going around it. And that is the circumcircle for this triangle. And so center of that circle, let it be O. So that is the circumcenter of this triangle. And so angle BAC is A. What will be angle BOC? 2A. Angle at the center is twice angle on the segment. We know that. So the sides are ABC, vertices are ABC. Now, if angle at this BOC is A, then angle BOD would be A and DOC would be A. From O, we draw a line perpendicular to BC. That will bisect BC. The two triangles are congruent. So we have two angles A and A sitting here. So what is sine of angle DOC? A by 2 by R, opposite by hypotenuse. Or sine A is A by 2R. Or A by sine A is 2R. If A by sine A is 2R, B by sine B, C by sine C will all be 2R. That is the proof for A by sine A equals B by sine B equals C by sine C is equal to 2R. Find the sine rule, you prove it by saying, let us draw the circumcircle and then simplify after that. Let's go back to area of a triangle. We know area of a triangle is half into base into height. So if you take this triangle, area of a triangle is half into BC into AD. If AD were h, some height h. Right? So look at triangle ADB. What is sine of angle B? Sine angle B, when you look at triangle ADB, h by C, or h is C sine B, or area is half AC sine B. Half into BC into AD is half AC sine B. All we do is draw the altitude and use 1 unit of trigonometry. And so instead of saying AD, we call AD is C sine B. Sine B is AD by C, or AD is C sine B, half AC sine B. Therefore, half BC sine A, half AB sine C, etc., etc., etc. And so half into side, a product of two sides of a triangle and sine of the angle in between them. Area is half into AC sine B. Sine B is B by 2R. You plug that in, you get ABC by 4R. And we know sine rule from sine rule, B by sine B is 2R, or sine B is B by 2R. Half AC sine B is the area, half AC into B by 2R, which gives us ABC by 4R. We're just linking up the different formulae for this. Okay. So it's a very interesting idea. We know that area of a triangle is half into base into height. So for this triangle ABC, which is a general random obscure scalene triangle, we draw the inner circle with center I and radius R. So forget about the triangle ABC. What is area of triangle BIC? So triangle BIC, what will be the area? Half into R into A. ID is perpendicular to BC, tangent perpendicular to radius. So you draw perpendicular from I to BC. Half into base into height is half AR. What is the area of triangle AIC? Half BR. AIB, half CR. So now we've got that. So if we add all three of them up, we'll get half AR plus half BR plus half CR, which is nothing but area of triangle ABC. Half AR plus half BR plus half CR is nothing but R into A plus B plus C by 2, which is RS. And area of a triangle is R into S, which is radius into semi-perimeter, which is nothing but half into base into height through some other context. So we've just linked up all the bits and bobs with different formulae for area of a triangle in one place. And so it's a very useful exercise to link this up. I want you to do one more thing. Suppose you have this formula ABC by 4R. What is the area of an equilateral triangle of side A? Root 3 by 4A square. Suppose you have forgotten what is circumradius. You can say A into A by 4R is equal to root 3 by 4A square. And then solve and get R. What will you get for R? What is circumradius of equilateral triangle of side A? A by root 3. Or you put R into 3A by 2 is root 3 by 4A square. You get in radius. So anytime you're stuck somewhere, you can figure that out by coming back to the starting point. And so RS is area of a right angle triangle. For a right angle triangle with sides A, B, and H, what is in radius? A plus B minus H by 2. Semi-perimeter? A plus B plus H by 2. Multiply these two, you'll get the area. So you can use this to cross-link all of those parts. Equilateral triangle, isosceles triangle, right angle triangle, and then combine all of them and then simplify. And so with that, we're pretty much done with all the theory. So I'm going to revert to the questions part. So we'll continue where we left off. This way we're not rushing the theory part. Give me a second, we'll read that question and we'll start up with that. Give this a go. Consider a right angle triangle with in radius 2 and circumradius of 7. What is the area of the triangle? Right angle triangle with in radius 2 and circumradius 7. Circumradius is 7. What does that give us? Hypotenuse is 14. It's a wonderful, juicy method of solving this. We've actually solved this by one elaborate roundabout method. Then Arvind fixed it. So I'm going to do it by the juicy short method. So try to see if we can find that. Hypotenuse is 14. That much we know. Then work with that. In radius is 2. What does that give us?
A plus B is equal to 18.
A plus B minus H by 2 is 2. Or A plus B minus 14 is 4. A plus B is 18. We know A plus B, we know H, we know in radius. How do you find area? R into S. You can technically do Pythagoras theorem, find A and B and then do all that. Area is RS. In radius is 2. If you know semi-perimeter, we are through. If you know perimeter, we are through. You're looking to find A plus B plus H. A plus B is 18. H is A plus B plus H 32. Perimeter is 32. Semi-perimeter 16. R into S 16 into 2 32. So you know semi-perimeter, you know in radius. So you're asked for area and you know in radius. You tell yourself, if I find the perimeter, I'm through. I don't need to find more than that. You've been given hypotenuse. So if we find A plus B, we're through. I'm not saying you've been given hypotenuse. You've been given circumradius, which means you've been given hypotenuse. You should know that. Circumradius is half of hypotenuse. You're looking at a right angle triangle. Fine. So for this, hypotenuse is 14. A plus B is 18. So perimeter is 32. Semi-perimeter is 16. R into S, 2 into 16, 32. We've actually done this by a more roundabout method. We'll fix that later on. Go to the next question out there. Give this a go. ABCDE is a regular pentagon. O is a point inside the pentagon such that AOB is an equilateral triangle. What is angle OEA? Very good question. Typical of what you'll find in the exam. Very doable, but only when you know the basic fundamentals. You can fully expect a question like this, and very doable question. I hope I've loaded on the pressure. What is each internal angle in a regular pentagon? Internal, 108. Each angle in an equilateral triangle? You know, equilateral triangle? 60. So wonderful question. If you mark everything you know on the diagram, the answer just jumps out. I've laid out everything you want in the diagram, and the diagram is a big giveaway. Triangle OAB is equilateral. That's been given. It's one other wonderful triangle. What can you say about triangle AEO? And you're done. We know this angle here is 60. So what is this angle OAE? Angle OAE is 48. Angle AEO and AOE are equal. 48 plus 2x should be equal to 180. Find x here too. And so angle OAB is 60. That we know. Internal angle in a pentagon is 108. That we know. Therefore, angle EAO is 48. That we know. Triangle EAO is isosceles. This angle is 48. Other two angles are equal. 48 plus 2x is 180. 2x is 132. X is 66. A wonderful question. You will definitely get questions like this, where you just know simple funda. Sum of all internal angles is 360. Sorry, external angles is 360. So outside is 72. Inside is 108. That you should know. Equilateral triangle 60. That we know. Remaining is 48. That we know. This triangle AEO is isosceles. We know that. And then you're done. Just writing down the answer. And wonderful question. Very typical of what you'll find in the exam. Next one again is one of my favorite questions. Give it a go. We'll discuss that. Classic question. Wonderful question. Give it a go. It's one of the juicy questions where you can do it by an elaborate method, which is the most obvious direct method. But you reject this, you're writing down the answer in seconds. And we know that area of this triangle is maximum. So half into base into height should be as high as possible. But how do we find the height? We can't find that. R into S, we can't find. ABC by 4R, we can't use. We're down to square root of S into S minus A into S minus B into S minus C. We have to maximize that equation in X, which is obviously tough. Right? So what do? What is the other formula for area of a triangle? Heron's formula, not getting us anywhere. Half into BC sin A. So forget X. Two sides of this triangle are 6 and 10. Anyway, don't know X. So half into 6 into 10 into sine of the angle. And 90. So this has got to be a right angle triangle for us to work. Therefore, what is X?
8.
I was hoping somebody would say 8. It is not 8. Why is it not 8? So the angle between 6 and 10 is 90 degrees. It is the product of two sides and the angle in between the two sides. So this is a right angle triangle, all right. But it is a right angle triangle where the two sides are 6 and 10. So X would be square root of 10 square plus 6 square, which is square root of 136. So none of these. It is not 8. So even after you get the funda and you mark 8, you've just taken a lot of effort to get -1. Fine. So be very careful. It is half into product of sides and sine of the angle in between them. And so better off leaving this question. So sine of the angle in between them. So use Heron's formula. It's a wild goose chase. You'll be trying to maximize a quadratic. Just doesn't work. Not worth it. Not worth doing that question. And so the key point here is think of area as that other formula. Half BC sin A. Half into 6 into 10 into sine of angle in between that. Therefore, it has to be maximum. Then that angle between 6 and 10 has to be 90 degrees. You know that is 90 degrees. You're looking at a right angle triangle with side 6 and 10. With side 6 and 10, or not side 6 and hypotenuse 10. Just remember that. So X is square root of 136. Not there, none of these. In wonderful question, give it a go. Again, a wonderful question. I'm not going to give you the answer. It takes a while. Spend time on it. I'm going to give just the starting step. Forget this ratio of 1:1:m, the ratio of the angles. Ratio of angles can be anything. You can have angles in the ratio 1:1:300. This can still a possible triangle. And so work only with 1:1:√n. And so remember, there's one wonderful property with sides of a triangle. So if ratio of sides is 1:1:√n, you can find what possible values of n are there. What are the possible values of n? Can n be 100? 1:1:√100. Can ratio of sides of a triangle be 1:1:10? Not possible. Sum of two sides has got to be greater than the third side. Completely forget about m. Just find possible values for m. Sorry, completely forget about m. Find possible values for n. Work with ratio of sides of the triangle. Ratio of sides is 1:1:√n. Find what values n can take. And so once you've got that, then worry about m. So now that you've forgotten about m, what values can n take? 1:1:√n. N can be 1, it can be 2, it can be 3, it can be 4. Only 1, 2, and 3. So forgetting about even angles, only 3 possible triangles that are there. 1:1:√1, 1:1:√2, 1:1:√3. 1:1:√1. What triangle is it? Equilateral. In which case, what will be m? So it could be 1:1:1, 1:1:1. Is that possible? So why is it not possible? Distinct natural numbers, so that's out. So that 1, 1 solution is out. So n equal to 2, 1:1:√2. Sides are in the ratio 1:1:√2. What type of triangle is it? Isosceles right angle triangle. So angles will be in the ratio 1:1:2. So n could be 2, M could be 2. Again, dead end. Those two don't work. They're out. So we're down to 1:1 root 3. So 1:1 root 3. The question is telling us in some form that there is a natural number M for which 1:1 M works. Now find that. So he's saying find M plus N. He's not saying how many such triangles are possible. Then it could be 0. Basically, the question is telling us that you found there are 3 values of N. 2 of them don't work. The third one does work. So find M for that third triangle. So now draw this triangle where sides are in the ratio of 1:1 root 3. It's an isosceles triangle. We know that. Find the angles of that triangle. Therefore, we can find M from there. The question is saying that triangle exists and it has a proper M, which is a natural number. So we know that. Now we can confidently say I'll find that M. So go for this triangle, draw this triangle, which is 1:1 root 3. And then say, look, I'm going to find some way of finding this angle. Use some trigonometry. The 1:1 root 3 triangle is an isosceles triangle. It's an isosceles triangle where the way I have drawn it, AB is equal to AC 1 and 1. BC is root 3. If we draw the altitude AD, DC would be root 3 by 2. What is this angle DAC? DAC is 60. Why 60? How 60? Sine 60 is root 3 by 2. So that angle is 60. So angle BAC 120. So ratio of the angles is 1:1 30, 30, 120, 1:1 4. So when N is equal to 3, M has got to be 4. M plus N. Wonderful question, tough question. When start with N and say N can only be 1, 2, 3. If N is 1, M is 1. If N is 2, M is 2. Both dead ends. We cannot take it because we're talking about distinct natural numbers. This is telling us that when N is 3, M not only exists, M is not 3. That much we know. So M is some other angle. So we need to draw this 1:1 root 3 triangle and then say, look, I'm going to try to find the angles in this triangle. As it turns out, the angles are 30, 30, 120, 1:1 4. Now you know that 120, 30, 30 triangle has sides in the ratio 1:1 root 3. Try this one. Again, doable question. The same triangle that we have seen right now. Obviously, once again, for this question, we'll need to know some amount of trigonometry, and it helps. An isosceles triangle with one angle 120. That means the other two angles are 30 and 30. Two sides are equal. So once you draw the triangle, you can find the equal sides. This angle is 120. Area is 16 root 3. So what is sine 120? Root 3 by 2. So these two are equal. So area is nothing but, if you call, this is x, this is x, half into x into x into root 3 by 2 equals 16 root 3. Root 3 gets knocked off. 16 into 2 is x square, or x should be 16 into 4, 64 is x square, x is 8. So two sides are 8 and 8. Third side should be 8 root 3. So you're looking at 16 plus 8 root 3. So that the formula that half into product of sides into sine of angle between them being area is very useful. Area is 16 root 3. Half into x into root 3 by 2. Sine 120 is 16 root 3. Cancel that, you'll get x as 8. We've just now seen that in an isosceles right angle triangle with sides 120, 30, 30, the sides are in the ratio 1:1 root 3. So sides will be 8, 8, 8 root 3. You have two sides 8, third side 8 root 3. Perimeter is 16 plus 8 root 3. And half into product of sides into sine of angle between them. That being area, remember that. Somewhere it will just come in very handy, stick it and get it. A very tough question. Try it for some time. It's going to be based on one idea, which might come of use, probably tougher than what we'll see in the exam. Give it a go, then we'll discuss that idea. It's a very tough question. I'm going to give you a clue. And so again, using the area idea that area is half into product of sides into sine of the angle in between. The additional clue, sine theta is same as sine of 180 minus theta. And sine x is sine of 180 minus x. Use that somewhere. And area of any triangle ABC is any triangle is product of two sides, half into product of two sides into sine of angle in between. Very unlikely that we'll get a question based on this idea. It's a juicy idea, so let's just add that on to this. I'm going to jump in and solve this wonderful question. Again, tough question based on that one idea, which is not likely to be tested, but it just complete this for any which way. And so, if you look at triangle AOB, BOC, COD, and DOA, mark the diagonal, the segments of the diagonal AO, BO, CO, and DO at X, Y, Z, and P. And so, area of triangle AOB is half into X into Y sine of angle AOB. Area of triangle BOC is half YZ sine of angle BOC. COD is half ZP sine of angle COD. Remember that two of these angles are equal. The other two are equal to 180 minus this. So sine angle AOB will be equal to sine angle COD, will be equal to sine angle BOC, will be equal to sine angle AOD. And so now comes the tricky part. We still have this X, Y, Z piece to deal with. And so, but think about this. This top triangle is going to have X into Y. This is going to have Z into P. This has X into P. This has Y into Z. So if you multiply the areas of these two and multiply the areas of these two, both of them should be equal. So if you have a quadrilateral and the diagonals cut the quadrilateral into four triangles, there'll be four triangles. The opposite sides areas, if you multiply, they'll have to be equal for all of them. Because you'll have X, Y, Z, P coming in both places. There'll be half and half coming in both places. There'll be two sines coming in both places. The sines are equal. We have X, P, Z, Y coming in all sides. Therefore, product of these two, 12 into 20 is equal to 15 into X. Once you know that, you're done. And so if this sine is M, then M gets cancelled on both sides. So 12 into 20 is 15 into this area. Or area of triangle AOB is 12 into 20 by 15, which is 12 into 20, 240 by 15, which is 16 units. And so any triangle we have, any quadrilateral we have, we break that product of area of the top two triangles will be equal to product of the two triangles on right and left. Top and bottom, if you multiply, that area should be equal to product of right and left. Why that is true is what we have seen just now. Based on the sine rule formula, half AB sine C, and the idea that sine X is equal to sine of 180 minus X. So sine for all four of them is equal. That's how the product part get cancelled. So using that, we can find area of triangle AOD to be 16. We know all four areas, 12, 15, 20, and 16, add them up and find the area of the quadrant. Let me just see. It's a tough question. Give it a go. This will probably be the last of the tough questions we do. And then we'll go on to simpler, more relevant question. It's a fun question, so give it a go. But properly tough question, so take your time. Take your time and give it a go. From now on, we'll start doing more and more relevant questions. Leave the really tough ones out. This is even the last question. The idea was might come of use somewhere. This one is properly tough. Useful question, but very unlikely that we'll get a question this tough. Yep. See, if you assume it's a square, then all four small triangles area should be equal. In any square, if you draw the two diagonals, the diagonals are equal, they bisect, they're perpendicular. So all four areas will be equal. If you assume it's a rhombus, again all four areas will be equal. Rectangle, all four areas will be equal. If you assume it's a parallelogram, two sets of areas will be equal. In the sense that you cannot make any of those assumptions because it's inconsistent with the rest of the data. In any rectangle, the right and left will be equal, top and bottom will be equal. Here, three triangles have been given, and all three have different areas, so we cannot make that simplifying assumption. This again is a tough question. Give it a go. We'll solve this question to see how we can use Pythagoras theorem in different contexts, but tougher than what you'll see in the exam. Clearly tougher than what you'll see in the exam. After this, we'll jump over and shift out. We'll shift out to simpler questions. We'll also try to do questions using on trigonometry, mensuration, and coordinate geometry. The diagram is also tricky, so I'm going to just show the diagram and then we'll continue to crack it, continue to try it. There's a big square, and then in between the big square and the circle, in that segment, we draw a small square. And so circle with center O is a big square, and we're trying to construct a small square. Just remember that even though this diagram is not making it obvious, that the shape LMNR is a square. That there is an arc Rn and a side Rn. Okay, so this part here, right at the bottom that you're looking at, that looks like the arc and line are merged because you're talking about a square in that small place. And there is an arc Rn and a straight line Rn. There's an Rn which is a chord. There's an Rn which is an arc. So remember that it seems like that gap is not visible, but that is there. So keep that in mind. So circle involved and a square involved, lot of right angle triangles. You're going to use Pythagoras theorem somewhere. If you think of the radius of the circle to be r, then the diagonal of the square is 2r, or side of the square is r root 2. In all of these questions, we're saying we have to link the radius of the circle to side of the smaller square. Assume side of the smaller square to be a, radius of the circle to be r. Keep marking stuff in both terms wherever possible. And somewhere you'll find something where you can write an equation using a and r, solve that and get a ratio a by r or r by a. So in this case, we say if you say side of the circle, the radius of the circle is r, then diagonal of the larger square is 2r. So side of the larger square is r root 2. So this OP is r root 2 by 2 or r by root 2. Now coming to the smaller square, LM, NR, LM is A, MR is A, RN is A, PQ is A, RQ is A by 2. As much as possible, mark lengths on the diagram in terms of A or in terms of R. So we can find OP on side of the square, diagonal of the square, all of those in terms of R. You can find everything related to the smaller square in terms of A and A by 2 in terms of A. Then see if you can mix something up. There's one particular right angle triangle which is very exciting, which is very interesting to pick on. Which is that one? You want a right triangle which has some sides marked in terms of A, some marked in terms of R, so that you can use Pythagoras theorem and then simplify and do something with that. Which is the one right triangle that can open this up? R? RQ? RQP, everything is in terms of A. RQ is A by 2, PQ is A, so you can find RP in terms of A. That doesn't give us anything. We want to link A and R. Sorry, NM and MP and O. Sorry, NP and O. LPO, okay. L is A by 2. OP is R by root 2. There's no way of writing OL in terms of anything. We'll find OL, but that's not taking us anywhere. We'll find OL using Pythagoras theorem.
What about, we know that OQ is the radius.
OQ is not the radius. Q is on Rn, which is a straight line. OQ is not the radius. Q does not lie on the circle. Q lies on Rn.
This one, the vertex one, O, P, and that vertex. So
O?
minus
So O,
P,
O, P and A for the triangle. And 1 is to 1 is to root 2. Everything in terms of R. How do we include A into it? If you take the square as ABCD, OPA, OPB, OPC, whatever it is, R 1 is to 1 is to root 2. You're not getting anything with A. Sorry? P, Q, okay, and one vertex of the square, okay.
So
PQA.
you have that in terms of R, the side of the square in terms of R,
Correct.
and you can solve for
You can solve, but you don't know anything about the hypotenuse. What you're saying effectively is, suppose you're saying A, B, C, D. If you join Q to C, we'll get QC in terms of R and A. What are we going to solve? You need all three in terms of R and A so that you can solve and get something. O, R, Q. RQ is A by 2. What is OR?
radius.
R. Okay. What about OQ? R by root 2 plus A. Perfect. So you're chasing this triangle OQR. ORQ. OR is the hypotenuse which measures R. RQ is A by 2. OQ is OP plus PQ. R by root 2 plus A. Take that right triangle where all three are in terms of R and A. Plug Pythagoras theorem and we're done. We're looking at triangle OQR. OQ square plus QR square equal to OR square. So R by root 2 plus A the whole square plus A by 2 the whole square equals R square. Simplify this, we'll get something in terms of. We need to find R by A or A by R, one of the two. Whatever we need to find, we can find that. So divide throughout by R square, we'll get A by R as an expression. Solve that, we are through with it. So give that a go, even the solving part of stuff. When you'll get an equation in terms of R and A, we need to find A by R. So divide that equation by R square throughout. So you'll get a quadratic in A by R. Call that as X. Solve that quadratic, you've got the answer. Very tough question, even the algebra part of it. Because you'll have to say R by root 2 plus A the whole square plus a by 2 whole square equals r square. So you'll have r square terms, ar terms, and a square terms. So divide throughout by r square, you get a by r terms. Call that as x and then simplify that. So we get 2r square minus 4ar root 2 minus 5a square is 0. Or if you solve this, you get a by r is root 2 by 5. So a is to r is root 2 is to 5. Obviously a very tough question. Unlikely that you will get questions like this. Definitely not. Very, very unlikely. But that idea where you're saying, look, I'm going to look for a Pythagoras theorem. I'm going to go searching for a right angle triangle where the sides can be described in terms of r and a, and then plug the Pythagoras theorem in and get out. That idea is important. Because we are pretty much done with all the ideas in geometry. Spend more time on triangles and circles, less so on quadrilaterals and polygons. Spend a lot of time on equilateral triangle, circle, square, and equilateral triangle inside circle, circle inside equilateral triangle, square inside circle, circle inside square. Those variants. You should know everything about the wonderfully, perfectly symmetric figures. If you know that, then everything else becomes much simpler. So keep that in mind. So chase complete understanding of the symmetric shape. Very vital. I'm going to move over. I'm going to see if we can do some other questions. Try this question. Give it a go. We'll discuss that. We're shifting to coordinate geometry. We're going to do a little bit of coordinate geometry, a little bit of trigonometry and mensuration, and then see if we have time to come back to geometry and round it off. So try this question. Good question. Give it a go. We'll discuss that. Questions like this are possible. This one very, very important funda working here. Looking at modulus of x minus 2 plus modulus of y plus 4 less than 5. Anytime you find something in terms of x minus 2 and y plus 4, x plus 5 and y minus 3, an equation in terms of that, you can forget that x minus 2, y plus 4. Just think of it as x and y at that point 2 comma minus 4. And this question is nothing at but mod x plus mod y less than 5. Instead of around 0 comma 0, it is around the point 2 comma minus 4. The idea of saying I'm not imagining this diagram around the origin. I'm just going to imagine this diagram around that point, but I don't want to solve for modulus of x minus 2 plus modulus of y plus 4. I'm going to think of this as mod x plus mod y less than 5. or mod h plus mod k less than 5. So whenever you're dealing with x minus 5 instead of x throughout, y plus 3 instead of y throughout, you can ignore that and say, look, I'm going to forget this minus and plus. I'm going to think of this as just mod x plus mod y, draw this diagram. Whatever diagram I've got, that same diagram shifted to this point 2 comma minus 4 is what I'm looking at finally. And so don't try to draw by selecting a lot of points and values and constructing this around that point 2 comma minus 4. So this question is practically same as mod x plus mod y less than 5. Draw that shape, imagine that, find the area, and then say everything I have found, I'm solving this completely around 0 comma 0. If I have this shape for which I've already found the area and just shifted it out to this point, that's what the question is asking. As far as the area is concerned, you don't even have to shift it out to that point. You have a certain shape. How does it matter where it is? Area is going to be the same. This question answer is exactly same as solving for mod x plus mod y less than 5. That idea is very vital. All we are doing is selecting this pot, that whatever that shape is, mod x plus mod y less than 5, and then shifting it out and placing it somewhere else. When you're saying modulus of x minus 2, modulus of y plus 4, basically saying instead of this, I'll do mod x plus mod y, find wherever it is, and then shift it out to that different point. And that funda of saying using a minus 2 and a plus 4 just shifts it out. That is very vital. So this question practically boils down to mod x plus mod y less than 5. That you should be able to draw and solve and simplify. So try that question. Still a tough question. You still have to solve to find the area of mod x plus mod y less than 5. Imagine how the diagram will be. Anytime you're solving for drawing anything for an inequality, forget the inequality. Call it equal to. You're thinking about mod x plus mod y equal to 5. Draw that. And then the region will be to the left of that or to the right of that. That you can figure out later on. So don't worry. If you're saying solve for the equation 2x plus 3y less than 5, forget it. Solve for 2x plus 3y equal to 5. And then either to the left of that line or right of that line is what you're looking for. Anytime you're solving for an inequality in shapes in coordinate geometry, solve for the equality. Then think about what the inequality means. So effectively, this question now translates to draw the shape for mod x plus mod y equal to 5. How do I do that? Anytime you're solving anything in coordinate geometry where you have to imagine a shape, put x equal to 0, find y, put y equal to 0, find x. Find the points on the axis that make sense for this. Once you have found that, move on to other things. So put x equal to y, 0, find what points of y exist. Put y equal to 0, find what points of x exist. Then think about what shape this could be, how it can be constructed, all of that. So try that. Try this question.
Sir, this type of equations come, so you always be some sort of quadrilateral only.
We're talking about linear equation. So mod x plus mod y equal to 5. Remember, mod x is x when x is positive. It is minus x when x is negative. So if you do this quadrant by quadrant, you're going to get x plus y equal to 5, x minus y equal to 5, y minus x equal to 5, minus x minus y equal to 5, some equation like that. So effectively, wherever you do it, whatever condition you do it, you're going to get straight lines. So this is a set of straight lines. So it becomes easy to imagine. You have 4 straight lines in 4 quadrants, meeting at pi comma 0, 0 comma 5, minus pi comma 0, 0 comma minus 5. Connect them, you've got the shape. If x square, y square are involved, then you're worrying about circles. If x into y is involved, it's weird shape. As far as our exam is concerned, you can take it for granted 90% chance that you're dealing with straight lines and a 9.9% extra chance that you're dealing with circles, if not, nothing else. You'll not get parabola, hyperbola, and all that. None of that. Ellipse, parabola, hyperbola, weird shape, curve, none of that. Don't even bother touching any of that. If you're looking at any shape in your exam, you're saying, look, a bunch of straight lines, I'm going to find that. If not, then you're looking for a circle. And so don't go around looking for non-existent, really tough shape. It won't come. So you can look at the question and say, bunch of straight lines, I'm going to find that straight line. That's what you're looking for. And so in this case, it's a bunch of straight lines around that point, 0, comma 0. How do I find the straight lines? I know I'm looking for straight lines. I put x equal to 0, we get y to be 5 or minus 5. You put y equal to 0, find x equal to 5 or minus 5. Or the points are 0, comma 5, 0, comma minus 5, 5, comma 0, minus 5, comma 0. And 4 straight lines in 4 quadrants. So you get a shape like this, which looks like a rhombus. It's actually a square. It's simpler than a rhombus. It's a square. Square of side 5 root 2. Or area of the square will be 5 root 2 into 5 root 2, 50 square units. And really tough question. We're doing this because there's a bunch of ideas involved. First one, if you get this x minus 2, y plus 4, that type of equation, forget the minus 2, forget the plus 4, do it around the origin, the simpler version, and then say, look, I found this whole thing, I'm just shifting it out. And that's the first simplification. Anytime you have to draw a new shape, find a bunch of points, then we can worry about the drawing part. We'll connect those points together. How do you find points? Put x equal to 0, find y, put y equal to 0, find x. So you know where it cuts the axis. And once we know where it cuts the axis, then simpler. And you can work around that. These are 4 straight lines. They're straight lines, and we have 4 meeting points on where it cuts the axis. If you put the 4 points and say I'm connecting straight line, you'll end up drawing this diagram. Right? Once you've drawn the diagram, it's a square. Area is product of the 2 sides, 5 root 2 into 5 root 2, which is 50 square units, whatever choice that is. Right? Let's go to the next one. Very good question. Again, very much possible that you'll get a question like this. Take your time and draw this diagram. Take your time. Every time you're looking to draw a diagram on coordinate geometry, undoubtedly plug x equal to 0, y equal to 0, find the other point, put 1, put x equal to 1, find the point, put y equal to 2, find the point. Find a bunch of points, then think of the diagram. Area enclosed in the region defined by y equal to modulus of x minus 1 plus 2, x equal to 1, x-axis and y-axis. X-axis and y-axis are very easy to imagine. The line x equal to 1 is very simple. We know how to do that. X equal to 1? Line parallel to axis. So we know that. So now the only shape that you have to draw is y equal to modulus of x minus 1 plus 2. For imagining that shape, simplify your life. Draw y equal to modulus of x minus 1 plus 2 will come to later on. For that, simplify life. Draw y equal to modulus of x. Modulus of x minus 1 will come to later on. So go step by step. If you know what is y equal to mod x, then it's simpler to think about what is y equal to mod of x minus 1. 10 plus 2. You can go there. Substitute x equal to 1 in this equation, find y. X equal to 0, find y. Y equal to 0, find x. Play around with some numbers, then you can simplify this. Will y ever be 0? There's no y equal to 0 for this. This graph simply does not touch the x-axis. Modulus of x minus 1 cannot be negative. Y is more than 2. This is higher up. This is above the x-axis. Y cannot be negative. Y cannot be less than 2. Y is equal to modulus of x looks like this. Y equal to x is a line which goes through the origin under the first quadrant like that. Y equal to modulus of x, mirror image this side as well. The 45-degree line from the origin in the first quadrant and the second quadrant. That is what y equal to mod x stands for. Okay. Y equal to x is a simple line, straight line passing through the origin. Y equal to minus x, a straight line passing through the origin from this side, from second quadrant to fourth quadrant. Combine both of that, we get y equal to mod x. And it's only positive, goes to 0 only at 0. That's the line we're looking at. Suppose we did y equal to modulus of x minus 1. All that mean? The whole thing will shift to the right by 1 unit. So y equal to modulus of x minus 1 will look like this. When x is 1, this will go to 0. We're shifting it right. Y equal to modulus of x minus 1 plus 2. That will go up like this. Now we can find the other points as well. We can say, look, where does it cut the y-axis? That point where x equal to 0, what happens to that? So we can find those points. So this point, the bottom here is 1, 2. X coordinate is 1, y coordinate is 2. Well, where will be the line x equal to 1? So at the point of intersection at bottom, we get just like this. So we need to find area of the shaded region. X-axis, y-axis, the line x equal to 1, and this shape given by y equal to modulus of x minus 1 plus 2. What kind of shape is this? Trapezium. Or you can say it's a triangle and a rectangle. Half into base into height and that rectangle. Once you've got this far, do it carefully, mechanically, but you'll get the answer. The rectangle area, 1 into 2. Triangle area, 1 by 2, 2.5. You can treat it as a trapezium, or you can say, I'll treat it as a rectangle and a right triangle. Then you can simplify that after that. I'm not doing the actual solving part. The funda is important. If you've got this far, you can write the answer down. In your exam, there's every chance that you'll be given that diagram also, and then that equation, and then you have to find the area of the shaded region. They would not have given you the coordinates. They'll give you the diagram, because you need to find where is the bottom, where it cuts the y-axis, what is meant by x equal to 1, all of that. They'll give you this equation and the diagram without giving the exact coordinate points. So you have to find the exact coordinate points, but then find the area after that. And so slightly tougher than what you'll see in the exam, but kind of questions where they outline a diagram and then have an enclosed area which you have to find the area for. That is par for the course. Let's go to the next one. Again, a very common type of question. So give it a read. We'll discuss this. This kind of question is very common. Find 1 unit of geometry, 1 unit of coordinate geometry, but otherwise very easy. The equation of the common chord between two intersecting circles is given by 2x plus 3y equal to 11. Which of the following could be the centers of the two circles? So being given equation of the common chord, we need to find which of the following could be centers of the two circles. They're already suggesting that you have to see the answer choices and go from it. You can't find the center of the two circles. Just been given equation of a common chord. There could be gazillion circles, pairs of circles for which some part of this line is a common chord. Right? So he's already saying, the question is hinting that look at the choices and then tell me where you're going. Right? So forget the coordinate geometry part of it. We'll come to that later on. There is a common chord for which you know the equation. The centers of two circles. What's the funda you're using to try to do this? Line joining. Line joining the two centers will be perpendicular to the common chord. Be perpendicular bisector of the common chord. But you've not been given the end points. You've been just given that line equation. Will be perpendicular to the common chord. So we're looking for a line that will be perpendicular to this. A line perpendicular to this. What is the other funda? What are we using? Product of the slope should be -1. What is the product of this line? The common chord. -2 by 3. 2x plus 3y equal to 1. Or it has 3y equals -2x plus something. Or y is -2 by 3x plus something. This slope is -2 by 3. So we're looking for the slope to be. Plug it in, you're done. So most of your questions, like in coordinate geometry, will be use the geometry funda, apply yourself, and then do some little bit of. You can find slopes of any of these. One of these 4 slopes is going to be 3 by 2. y2 minus y1 by x2 minus 1. x1 is going to be 3 by 2. That's your answer. Done. Right. So You have to get that far by using the geometry and funda part of it. And then the final plugging in part is very easy. Y2 minus y1 by x2 minus x1 part is very simple. Not rocket science. The key point here, the line joining the centers of two intersecting circles is perpendicular to the common chord. We've been given the common chord that has a slope of minus 2 by 3. So this line should have a slope of 3 by 2. Now let's go and try to crack it. You're done. And so one of these four is the answer. What's the answer? I'm going to skip this one. Over elaborate. Try this one. I'm going to shift to trigonometry as well. Try this. Give it a read. We'll discuss that. Tan part 2012x plus cot part 2012x is equal to 2. Let's start with this. First up, tan part 2012x. What does that give you? What 2012? So it's an even number. What does it mean? What does it mean? Tan part 2012x. What do we know straight away? It's always positive. Cot part 2012x is always positive. And so these are two positive numbers. Not just that, If tan 2012x is y, what is cot 2012x? So we have a scenario where y plus 1 by y is 2. Y and y is positive. So y plus 1 by y is equal to 2. What does it mean? Y is equal to 1. The minimum value of y plus 1 by y is 2 when y is positive. And if in that case, if y plus 1 by y is equal to 2, then y has to be 1. So this question immediately boils down to tan per 2012x has to be 1. Therefore, cot per 2012x should also be 1. What does it say about tan x? What is the value of tan x? Tan per 2012x should be 1. Tan x should be plus or minus 1. It could be plus 1 or minus 1. So effectively, this question boils down to from minus 2 pi to 2 pi, how many values of x will tan of x be plus 1 or minus 1? That's it. So in the first quadrant, in how many values will tan x be plus 1 or minus 1? Second quadrant, every quadrant will be one value where it's plus 1 or minus 1. How many? What's the answer totally? 8.
When your powers are even, these people can be treated as 0 to 4 pi.
Minus 2 pi to 2 pi, any which way, minus 2 pi to 2 pi can be written as 0 to 4 pi. All trigonometric ratios go in cycles of 2 pi. So minus 2 pi to 2 pi is same as 0 to 4 pi. Instead of this 2 pi, you're taking that 2 pi. That is fine. The next one. Let's start with this. If you've shifted to the next set of questions, we're doing slightly different questions. But this is a question that we've already discussed some template on. Give it a go. We'll discuss this and then move on after that. I'm going to probably start running short of time, so I'm going to pick and choose questions from now on. Try this one, and then we'll jump across to more juicier bits straight away. Triangle side 7, 8, and x is obtuse angle. How many integer values can x take? Look at the answer. What are we looking at? What's the method? Sum of squares of two sides, two shorter sides should be less than square of the longest side. What is the longest side for this? It could be x or it could be 8. So solve for both. We're done. So we say 7 square plus 8 square is less than x square, or 7 square plus x square is less than 8 square. Those are two bits you're solving for. Just remember one thing when you're solving for this, the final bit, it has to be a possible triangle. And so sum of two sides has got to be greater than the third side. So x can lie only between 2 and 14. Right away. 7 plus 8 is 15. X cannot be 15 or more. 8 minus 7 is 1. X cannot be 1 or less. So x lies between 2 and 14. That's a starting point. And then we say if x were the smaller side or 8 were the longer side, x square plus 7 square is less than 8 square. So x square plus 49 is less than 64. X square is less than 15, or x could be 3 or 2 values. So x can be 3 or 2. Integer values 3 and 2. The other part we're saying 7 square plus 8 square less than x square. So 7 square is 49 plus 64 is less than x square. 113 is less than x square. So x should be more than square root of 113. So starting from 11. So 11, 12, 13, 14. So it could be 2, 3 or 11, 12, 13, 14, 6 different values for x. Right? Bunch of these questions are similar to what we have seen. So I'm going to skip this and go towards the last two questions on our sheet. Not the last question, but the two before that. Consider a triangle ABC with altitudes AB, B, and CF meeting at H. If angle A were 70 degrees, find angle BHC. So angle between B, orthocenter, and C, find that angle. Triangle ABC, angle A is 70 degrees, find angle between B, orthocenter, and H, orthocenter and C. And again, jump in and solve this one. So 3 altitudes meet at H. So think of triangle BFC. This is right angle. This is C. So what is, if you take triangle BFC, this angle is B, what will be this angle? Angle FCB.
100 minus 110 minus
90 minus B. This is 90. This angle is B. The whole angle is B. I'm thinking of triangle FBC. So the angle FCB is 90 minus B. What is the angle EBC? This angle? 90 minus C. So what will be this angle? We take triangle HBC. 180 minus 90 minus B minus 90 minus C, which is B plus C. Angle A is 70. Angle B plus C should be? The other way of thinking about it is think about quadrilateral FAEH. All 4 angles should add up to 180 to add up to 360. These two are 90. So these two should add up to 180. This were 70. This should be 110. This is 110. This is 110. Vertically opposite angles. So think about quadrilateral FAEH. 2 angles are 90. The other 2 should add up to 180. Angle A is 70. So angle FHE should be 110. If FHE is 110, BHC is 110. And that's the other way of doing the same thing. So with orthocenter, you can find that angle between 2 vertices and at the orthocenter, that angle. Try this one. Very similar. It's a slightly different idea. Keep that a go. Here we want to find angle BIC. So this one. So what is angle IBC? This angle? This will be B by 2. This angle will be C by 2. So this angle is 180 minus B by 2 plus C by 2. What is B plus C? 180 minus A. Plug that in, you're done. So it is 180 minus A by 2, which finally results in 90 plus A by 2. So the top angle is 80. The angle here would be 90 plus 40, 130. The formula is angle BIC is 90 plus A by 2. Whatever angle A is, 90 plus A by 2 would be angle BIC. And angle at the in center would be 90 plus A by 2. That's the formula. What you've seen, we're just trying to derive that formula and simplify that. With that, we're pretty much done with all the solving part. We're going to do this one question. Try this, give this a go. We'll discuss that idea and then move to a bunch of points where we revise the theory. This again is standard fare. Square inside circle, circle inside square should be on top of it completely. Square inside circle, circle inside square is proper testing territory, so we should know everything about this. And so we're saying there's infinitely many squares, infinitely many circles, but all that is just some decoration around this question. If you find the ratio of one circle to one square, you're done. Everything else, the ratio will be same. So this question is just one thing. Whether you do it 1,000 times or 25 times, it doesn't matter. All we need to do is find one ratio, then we're done. And so I'm going to give you one very simple idea or shortcut for finding any ratio. See, anything with circle and square, circle inside square, square inside circle, the circle area will be linked to pi. And so if the square is bigger, that means the square sits outside, then ratio of areas will be 4:pi. Square is bigger, pi is roughly 3, so 4:pi. The square is smaller or the square is inside the circle, then ratio of circle to square will be pi:2. The circle anchored around pi. The square is bigger, the square should be 4. The square is smaller, square should be 2. And so the ratio is either 4:pi or pi:2, larger to smaller. Pi will obviously come only when the circle is involved, not when the square is involved. And so when the square is larger, area of the square would be 4, ratio of areas. Area would be 4 is to pi, square to circle. The square is smaller, then ratio of circle to square would be pi is to 2. And so here we are saying a circle is inscribed in a circle of radius 4 centimeters. The circle is bigger. So if you assume area of the circle to be pi, square area would be 2, pi is to 2. Every subsequent area would be in the ratio of pi is to 2. The final area ratio is pi is to 2. And that funda between square and circle, that little ratio there is very useful. Anchor your circle around pi. Square is larger, it is 4. Square is smaller, it is 2. The square is circumscribing, area of square is 4. The square is inscribed, area of square is 2. So 4 pi, pi is to 2. And done. Answer is pi is to 2. And so I'm going to do a very quick recap of a lot of geometry things in terms of a bunch of simple true or false statements. Just say 5-6 minutes where we can discuss all of these in one go. True or false? Circumcenter of a triangle can lie outside the triangle. True. Imagine a large circle and you stick in a triangle in one corner, one small area. For that tiny triangle, this circle is still the circumcircle. So circumcenter can lie outside. When will it lie outside? Or what type of triangle will it lie outside? An obtuse angle triangle. For an obtuse angle triangle, circumcenter will lie outside. Now, incircle and circumcircle are concentric for an equilateral triangle. Incenter is same as circumcenter is same as centroid is same as incenter, as orthocenter. We know that. So circumcenter and incenter are coincident. So circumcircle and incircle are concentric for an equilateral triangle. The circumcenter of a triangle lies outside the triangle. The orthocenter will lie inside the triangle. Circumcenter will lie outside only for an obtuse angle triangle. For any obtuse angle triangle, orthocenter will also lie outside. Simple rule. Incenter is center of the circle inside the triangle. Incenter should always lie inside. When each median is inside the triangle, so centroid will also be always inside. Centroid and incenter always inside. Orthocenter and circumcenter can lie outside. They lie outside for obtuse angle triangles. For acute angle triangles, all 4 will be inside. For right angle triangles, on the triangle. So on the triangle, on the vertex containing the right angle will be the orthocenter. On the hypotenuse will be the circumcenter. So circumcenter and orthocenter are inside for acute angle triangles, on the triangle for right angle triangles, and outside for obtuse angle triangles. In a right triangle, the orthocenter, circumcenter, and centroid are collinear. True? Why true? So orthocenter is the vertex containing the right angle. Circumcenter is the midpoint of hypotenuse. If you join these two, that's a median. Centroid will lie on the median. So orthocenter, circumcenter, and centroid are collinear for a right triangle. This is not true just for a right triangle. For any triangle, orthocenter, centroid, and circumcenter are collinear. The proof for that is far tougher. But for any triangle, orthocenter, circumcenter, and centroid are collinear. In an isosceles triangle, the circumcenter, orthocenter, centroid, and incenter are collinear. True. So for an isosceles triangle, from the unequal vertex, if you draw a line to be the altitude, that will also be the median, that will also be the perpendicular bisector, that will also be the angle bisector. From the other vertices, you'll have multiple lines. But from this base vertex, you'll have only one line. On that line, you'll have centroid, incenter, orthocenter, and circumcenter. There's only one line. So for an isosceles triangle, all 4 are collinear. For an equilateral triangle, all 4 are coincident. The same point will be all 4 for equilateral triangle. All 4 will lie on the same line for an isosceles triangle. Orthocenter, circumcenter, centroid, and incenter will be inside for an acute angle triangle. They'll all incenter and centroid are inside for all triangles. For obtuse angle triangle, circumcenter and orthocenter would be outside. For right angle triangle, they'll be on the triangle. So this as well. 2 circles that touch each other externally will have exactly 2 common tangents. They'll have 3 common tangents. 2 circles that have exactly 2 common tangents must have a common chord.
Yes.
Yes or no? Why false? They have exactly 2 common tangents. What does it mean? They're intersecting. They must have a common chord. True. Two circles that have exactly two common tangents must have a common chord. They're intersecting circles. A trapezoid inscribed inside a circle has to be an isosceles trapezoid. True. Trapezium, opposite sides are parallel. And so you know that the two bottom angle and a top angle will be supplementary. In a cyclic quadrilateral, opposite angles are supplementary. So the two top angles should be equal, two base angles should be equal, ergo isosceles trapezoid. And so a trapezoid inscribed inside a circle has to be an isosceles trapezoid. A parallelogram inscribed inside a circle has to be a square. Why not? Can be a rectangle. A parallelogram inscribed inside a circle has to be a rectangle. In a parallelogram, opposite angles are equal. In a cyclic quadrilateral, opposite angles are. So parallelogram inside a circle, opposite angle should be equal and supplementary. 90. Therefore, all four angles should be 90. It should be a rectangle. It need not be a square. A parallelogram inscribed inside a circle has to be a rectangle. It need not be a square. A parallelogram circumscribing a circle has to be a rhombus. Sum of pairs of opposite sides is equal in a circumscribing quadrilateral. So AB plus CD equal to AD plus BC. We know AB is equal to CD, BD equal to DC. Sorry, is AD equal to BC. Therefore, all four sides should be equal. It has got to be a rhombus. Just check this out. Two circles that touch each other externally will have three common tangents, not two. They have two common tangents. They must intersect with each other. Therefore, there is a common chord. Just recapping all of this. A trapezoid inside a circle has to be isosceles. AB is parallel to CD. So if angle DAB were x, angle ADC would be 180 minus x. We know that angle A is x, angle C should be 180 minus x. So two bottom angles are equal, two top angles are equal, isosceles trapezium. A parallelogram inscribed inside a circle has to be a square. It has to be a rectangle, not necessarily a square. I'm going to stop with that. These are available online any which way. I'm going to disengage this thing, the online part, and then we'll continue with this.